Again, Rn is the set consisting of all the vectors with n components. Okay, now the main thing we are going to do today is to define some operations on vectors. For numbers, we mentioned before, for numbers you can perform addition, subtraction, multiplication, and division on vectors and so on, right? Now we want to define some operations on vectors. Okay. The first two operations we want to define are addition and subtraction. Okay. If Rn is too abstract for you, you just imagine n value is 2 or 3. It doesn't matter. In most cases, we just talk about R2 or R3, so we can visualize many things, right? In R2 or R3, Rn represents the directed line segment. So basically, there's a connection between the geometric definition and the algebraic definition, right? So vector addition. You are given two vectors in Rn, in the same Rn. So by that we mean u and v, they have the same number of components. If you are given two vectors with the same number of components, and then we can define addition and the subtraction of two vectors. Addition is the operation. The answer, we can also call the answer the sum. Okay. Very shortly, I'm going to give you a particular cases to show you the meaning. And also, I want to go over the definition first. We concentrate on addition, subtraction, and scalar multiplication. Scalar multiplication is comparable to scalar multiplication on matrices. We can use a number to multiply a vector. The answer is a vector. For addition or subtraction, the definition is here. I forgot to mention. All we need is to add or subtract the corresponding components. The answer is a vector. Okay. And scalar multiplication, we can use a number to multiply a vector. The answer is a vector. All we need is to multiply all the components by the scalar, by the number. I will show you the meaning using some particular questions. So now let's say given two vectors in R2. So maybe for example, early, so right before the class I was trying to change some setting, and I cannot write on the slides, so I had to turn it back. Now for example, now suppose we are given two vectors in R2. Now let me try to use the same notation. Okay. Now for example, if we are given two vectors, so now let's say u, the vector u has the two components. So now let's say 1, -1, and v is a vector with two components. So now let's say 1, 2. Okay. These are the two vectors in R2. I'm going to use the notations like that to denote R2. Okay. The way to write R2 is kind of weird. If I type, I would type the boldface, but for handwriting, I cannot do boldface. I just write R2 that way. I'm trying to say you write two bars, so that's actually my boldface R. Actually, so most people still write R2 that way. Okay. Again, we are given two vectors in R2. We are given two-dimensional vector. We are given two-dimensional vectors. Okay. Actually, so sometimes I just say u and v are two-dimensional vectors. The name is not too precise, but when I say two-dimensional vectors, I mean the vectors in R2. Okay, now the main thing is how to add or how to subtract the vectors and how to perform a scalar multiplication of vectors. So how about I give you another number c, okay, so that I can mention c is a scalar, c is a number, so I can compare the notations and the operations with the things in the definition. Okay, so now let's say c is a number, so whatever number. So Now let's say -2. Okay. A scalar can be any real number. It can be 1, can be 2, can be -1, can be -2, can be 0.1, can be 1/2, can be pi, can be e. For the people who take calculus, if you don't, if you never took calculus, pi and e could be a little bit. At least you know pi, right? 3.14 or something. Okay. I'm trying to say a scalar can be any real number. Okay. Now we are going to define addition and subtraction. I will show you the meaning. So now let's say if I want you to compute u plus v, it's easy, right? I do want you to check if the addition is defined. The addition is defined only for two vectors with the same number of components. I mean, only if both vectors are in R2 or the same Rn in general, the addition is defined. Okay. The answer is a vector. It's easy, right? You just add the corresponding components. The first component is coming from 1 plus 1, the sum of the two first components in u and v, I think is 2, right? And likewise, the second component is 1. And then we can also define the difference between two vectors. We can also subtract two vectors. I was trying to say the same thing in two ways. The operation is called a subtraction. The answer is the difference. Okay. We're trying to get the difference between u and v, two vectors u and v. Okay. So anybody want to write the answer to u minus v? So just write the two components in order. Actually, I have been saying for a long time. I just one reason is I want to make sure you can hear me. So what's u minus v? Yeah, 0, 0, -3. 0, -3 is right. Okay. So thank you. Okay. So you can hear me. Okay, and then we can. Another thing we want to talk about is the scalar multiplication. The operation is called scalar multiplication. The answer is also called the scalar multiple of the scalar multiple. So basically, c times. Now let's compute c times v. Okay. C is a number, c is a scalar, a number. Okay. V is a vector in R2. So the answer is going to be a vector with two components. All we need is to multiply the two components by the scalar of c. C is -2. In this case, the two components are -2, -4. And by the way, for the vectors, we can also represent a vector using square brackets. So now let's say v can also be represented using square brackets. You include the two components in square brackets in order. The same thing. Okay. But you have to include brackets. Okay. So do not just write 1, 2. So the same for matrices. I think on the assignment or the quiz, I have seen people writing a matrix without including the brackets. That's not right. Okay. Okay, so we have seen the definition of addition and scalar multiplication. For the three questions on the screen, I really think they are simple. I do not have to make too many comments. Now look at question A. So in the question you are given two vectors in R3, right? Two vectors in R3, and then the answer is 7, 10, -2 as the three components. Again, you add the corresponding components, you have the answer. The answer to addition is called sum. The sum is also a vector in R3. Okay. So question B is designed for illustrating scalar multiplication. The same thing. In this case, the scalar is 4. Right. I don't know where my C is. Yeah, that's my problem. You have A, you have B, and then the next question is question D. Okay, you just imagine it's question C, the next question. The point I'm trying to make is that two vectors, if you see different number of components, is not defined. The addition is not defined. Simple, right? Simple enough. I really do not have to go over this in more details. Okay, now let's talk about the geometric meaning, the interpretation, how we interpret addition and the scalar multiplication geometrically. Okay. The interpretation is consistent with the interpretation in actually with the physical meaning. So can we talk about the physical meaning a little bit? So very shortly we are going to give a more precise definition. Okay. So now let's say if you have an object, okay, on some surface, you just imagine a plane as a surface. Okay. Can we talk about dragging? One force is dragging the object. Now let's say that way. I'm going to say the force F1. So the other force is dragging the object. So now let's say that way. Okay. I'm going to say the force F2. Okay. Actually, we're going to you learned in physics, and also you're going to see the vector addition. The vector addition is going to be consistent with the meaning in physics. Okay. You have two forces, F1 and F2. If you drag the object at the same time, effectively, I think you're going to see it's not too hard to understand, right? You're going to see the object is going that way, right? It's going that way. That way, it's going to be the sum of the two forces. Very shortly, we are going to have more precise interpretation of the meaning. Okay. I think for the geometric meaning, I want to use some questions on handout. Now we are talking about part 2. I think part 2, question 1 is simple. We did that already. Okay. We also did question B. I know why I use C in the course manual. My C is here. Okay. In question C, you can perform some mixed scalar multiplication and addition. Actually, so later on, you are going to see we are going to do many questions like this. The answer, you are going to see the expression in question C is called a linear combination. I said a linear combination. Okay. So don't worry about that for now. Okay, now let's work on question 2. So I think question 2 is designed to illustrate the geometric meaning of addition and the scalar multiplication. I'm going to copy the question on PowerPoint. Good enough. In question 2, I want you to do a few things. So we're going to draw some sketch. In question A, you can try it on your own. So we can compare the answers. Okay. Now look at question A. In question A, I want you to sketch the position vector u. U has two components, 1, 3. And by the way, we are talking about vectors in R2. So later on, we're going to generalize the conclusion. Okay. Now let's say in rectangular coordinate plane or Cartesian coordinate plane, we have x-axis, right? We have the origin, we have y-axis, and a position vector. Now let's recall the definition. A position vector is a vector with the initial point, the origin, with the origin as the initial point. So the origin has to be here. And the position vector, if you know the two components, and then you know the terminal point. Okay, the terminal point is the point with x coordinate of 1. So now let's say 1 is here, and y coordinate of 3. Now let's say 1, 2, and 3. 3 is here. So the terminal point is here. That's the vector u. U is a vector something like this. Okay. Yay. It's pretty straight. That's vector u. I'm going to label the vector u. Can I label u in here? Again, a position vector is a vector with the origin as initial point. And then we sketch the vector v. V is the vector with the two components, -3 and 2. It's also a position vector. Okay. Now let's say -1 is here, -2 is here, and -3 is here, and the 2. I'm talking about the second component. Okay. So the position vector v is kind of here, right? With the first component of 2. So basically a position vector. So these two numbers will give you the coordinates of the terminal point. Okay. So the terminal point has x coordinate of -3 and the y coordinate of 2. I believe the vector v is here. So that is the vector v. Illustration only. I think I drew the u better, but that's the vector v. Okay. Now in question C, we are going to we also want to sketch the vector u plus v. But before that, we need to add the two vectors. Okay. So A and B. So we're done A and B. Now we move on to C. Okay. So before we do question C, we have to compute the sum of the two vectors. So u plus v. All of you guys can do that. It's the vector with two components. So now let's say now let me copy the vectors. Okay. U plus v, u is the vector 1, 3 with two components of 1, 3, and the v, you cannot write one side using round bracket and the other side using square. V is the vector with two components, -3 and 2. So the answer, you add the corresponding components. The first component for u plus v is -2 and then 5. Right? 5 is the second component. I hope I have enough room for 5. Okay, now what we want to do is to sketch the vector with two components, -2 and 5. Okay, -2 is here. I need 5 on the vertical axis. I I need point representing 5 on vertical axis. Okay. So now let's say 5 is here, 3, 4, 5. Okay. Okay, on number line. So do not tell me it's not you guys. I have seen some other people in other classes so doing this. 1. So now let's say 2, 3. So do not label numbers like this. They're not reasonable, right? Okay. Of course, it's not you guys. Now we are trying to sketch the vector with 2 components, -2 and 5. Again, x coordinate of -2 is here, y coordinate of 5 is here. Okay, I believe the terminal point is kind of here. I mean, that is the position vector representing the sum of u and v. Okay, just write u plus v. Sorry, it's a little messy because I should have drawn the whole thing a little bit down, but I think you got the idea. Okay, now we're going to generalize this, but can anybody try to give me a description of u plus v in terms of u and v? If you are given a vector u, a vector v, how can we describe the sum of the two vectors u plus v?
It's the resultant vector.
Yeah, so that's the resulting vector, but how do we describe the location of this vector? Okay, I will give you a little more hint. Okay, you imagine you connect the terminal point of v and the terminal point of u plus v. I'm going to use the dotted line. Okay, and another dotted line connecting the terminal point of u and the terminal point of u plus v. So do you see you have a parallelogram? Actually, u plus v is the diagonal of the parallelogram. Okay, in general, it's always true. I'm going to summarize. Okay, in general, if you are given u and v, you do not have to use the position vectors. If the initial points of u and v are at the same point, and then using u and v, you can form a parallelogram. Does that make sense? And then the sum of the two vectors, is a diagonal of the parallelogram. If I did not say anything very perfectly, I think it's in the course manual. Okay. I think a better sketch is that. That is the vector. That is the. Are we doing the same question? I think we are doing the same question. They are not the same question. Sorry, they are not the same question. Okay. But I will show you the description right now. Okay. Now look at the screen. The PDF. On the PDF, you have the description of the geometric meaning of the sum of two vectors. It's true for any vectors in R2 or R3, or you imagine in any Rn. Actually, in any Rn it's true. Okay. If we interpret u and v as vectors having the same initial point, then the diagonal of the parallelogram with u and v as two adjacent sides, so that's more precise, represents u plus v. Okay, now let me tell you the meaning. Okay, wherever that u is, as long as u and v, and by the way, the sum is not dependent on the rectangular coordinate system. is independent on the system. Okay, so now let's say U is here. Now let's say U is here. Wherever U is, wherever V is, as long as you put U and V, as long as you put the initial points of U and V at the same point, and then we can have the sum of U and V. Okay, so now let's say if U is something like that, V is something like this, and then using U and V as two adjacent sides, you have a parallelogram. You can always do that, right? And then U plus V is going to be that diagonal, right? The same is true if U and V form an angle that is greater than 90 degrees. Now let's use a case something like this. I was trying to draw. Now let's do something like this. Wherever U is, wherever V is, you can always put U and V. You can always put the initial point of U and V at the same point, as long as okay. I will make my point. I will talk about a little bit more general case. Okay. Now let's say that's the vector U. So that's the vector V. How can we represent the sum of the two vectors? You can always move. Now let's recall, geometrically two vectors are equal if and only if they are in the same direction and having the same length. You can always move this vector V so that it has the same initial point as U. So I'm trying to say, move this vector V to here. I do not even want to change the notation. V and V are the same vector. They point in the same direction, having the same length, right? As long as you can put the two vectors having the same initial point, and then the sum of the two vectors is represented, and then you can form a parallelogram, right? So something like this. That is the vector U plus V. So geometrically. Again, it's more important to understand the geometric meaning. If you interpret the sum that way, and the rule is called the parallelogram. Okay. I'm pretty sure you learned that in physics. I think many of you guys are in physics, right? Alternatively, there's a triangle rule. You can also interpret the sum of the two vectors using in terms of a triangle. I'm going to make more comments in here. Okay, I'm going to make the connections between the two rules, parallelogram rule and the triangle. Okay. So now let's say U is here, and then so now let's say V is here. I'll try to make V a little bit at a better location. Okay. Any location is okay. So now let's say V is here. If you use the parallelogram rule, U plus V, to get U plus V, you form a parallelogram, something like that. Okay, and then U plus V is here. Actually, correspondingly, there's a triangle rule. We can also use a triangle to get the sum. I think for the people in physics, you know that. I'm pretty sure you know that. Okay. And now let's try to move this V to here. This V is actually the same as this V. Okay. In some cases, it's easier to interpret the sum using the triangle rule. Okay, now now the label is kind of weird, okay, it's okay. Okay, I'm going to relabel the vectors. That is the vector u, so that is the vector v. The vector v is actually the same as this vector v, so I'm going to move the vector v to here. So I'm going to shade the triangle you need, so the meaning is clear. Okay. Using the triangle rule, how can we describe the sum of the two vectors? One of the two vectors is u, okay? And then for vector v, you put the initial point at the location of the terminal point of u. I want to repeat, probably I said something wrong. You put the initial point at the location of the terminal point of u. Initial point of v is at the terminal point of u. And then you have a shaded triangle. So you see how to get u plus v, right? And then the other side, the direction is from the initial point of u to the terminal point of v. So it represents the sum. It's kind of okay. Now let me try to show you what I mean. So now let's say u is here. Let's say so v is something like that. How do you add the two vectors? You move vector v so that the two vectors are connected. By connected, I mean the terminal point of u is the same as the initial point of v, right? Something like that. And then I was trying to say that's vector u, so that's vector v, right? You make the two vectors connected, and then the vector with the initial point the same as the initial point of u, and the terminal point the same as the terminal point of v. That vector is u plus v. It's probably a little bit hard for me to describe, but the meaning is simple. You just connect the two vectors and then you can get the sum. Just remember that. So any questions on that? Should be simple. Okay. Okay. Now let's talk about the first question. Okay. The first question. You have an object. You drag the object. Okay. So now let's say, so that's force 1. We mentioned before, a force is considered as a vector, right? A vector represents a quantity with the direction, and a magnitude. Force is a quantity having a direction and a magnitude, right? Okay, so now let's say, so that's force 2, a little bit bigger. If you drag the same object, and then we can get effectively the object will move to whatever direction, to the direction of force 1 plus force 2. When I said plus, I mean a vector addition. Using the parallelogram rule, you have something like this. You form a parallelogram. Effectively, it's the same thing. It's equivalent that you drag the object using that force. That force is the force F1, so plus F2. Right. I'm trying to say the vector addition is consistent with what you learned in physics. I think the velocity or other things are the same thing. Okay, I really do not want to talk too much about physics, so that's not my job. Okay, so that's vector addition. Okay, now we move on to question D. We did question C, right? Now we move on to D. I will still put D on this slide. Scalar multiplication is easier to interpret. Okay, now in question D, we're trying to sketch the vector 2u. Can I just do the same thing on the same rectangular plane? Okay, I'm going to sketch 2u. Okay, but before that, I'm going to compute 2u first. Okay, now 2u. U is the vector 1, 3. You use a scalar of 2 to multiply u. I think you have the vector 2, 6 with 2 components, right? Now look at the mouse cursor. On the rectangular coordinate plane, it's easy to sketch 2, 6, right? I think 2, 6 is somewhere in here. You just we still do a position vector 2, 6. Okay. So that's the vector 2u. So can I just label it here? Now, how do you answer the second part of the question D? So what is the relation between 2u and u? To tell me a vector, you tell me two things: the direction and the length, right? The direction and the length will determine a vector. So 2u. Now let's do the direction first. Okay, 2u points in the same direction as u, right? And twice as long. As long as u, I mean. Easy, right? I'm going to ask you a question, so just tell me yes or no. Is a scalar multiple always in the same direction as the given vector? Is the yes, no? Is the
No.
no? A scalar multiple, the scalar can be a negative number. If the scalar is a negative number, then now let's move on to E. I think question E is designed for that purpose. Okay. In question E, we are trying to compute the scalar multiple of negative 2u. So negative 2 is the scalar, and then times u. So this time you are going to have the vector with the first component of negative 2, the second component of negative 6. Okay. That's a vector is in the reverse direction and twice as long. Okay. That's probably the vector, so negative 2u, if you know what I mean. Again, the scalar multiple, the geometric meaning has two cases. One case is the case when the scalar is positive. The other case is the case when the scalar is negative. The two cases are different. When the scalar is positive, the scalar multiple is in the same direction. Okay. And when the scalar is negative, the scalar multiple is in different direction, in reverse direction, I mean. Okay. Okay, now look at the summary. Okay, if C, the scalar, if C is positive, then the scalar product, the scalar multiple Cu, is a vector which points in the same direction and c times epsilon. I think you know the meaning. The other case is when c is negative. Okay. Now I want you to look at the last paragraph. So later on, we're going to use that. Two vectors u and v are parallel. It means one vector is a scalar multiple of the other. You just remember the condition when two vectors are parallel. Two vectors are parallel if one vector is a scalar multiple of the other. Actually, the condition is if and only if condition. We also call that condition necessary and sufficient condition. If and only if condition is also called necessary and sufficient condition. It's probably relevant to the next question. I think question 3 is very simple. It's very simple. I will see if I have the answers to those. Okay, now look at question A. Okay, I think the question is very simple. I just go over some key points. Okay, I will see if I can make some comments. U is a vector in R3, V is a vector in R3, so it's possible to compute that linear combination. I told you the term earlier, so later on we're going to see the term over and over again. A number times U and then plus another number times V is called a linear combination of U and V. The linear combination is simple to compute. 2U is in R3, right? 2, 3 is a vector with 3 components. 3v is a vector with 3 components, and then you can add the two vectors. The order of operation is the same as numbers. You perform scalar multiplication before addition. That's a comment I want to make. The only thing you need to know is perform scalar multiplications before addition. It's comparable to number addition, subtraction, and multiplication. Order of operation. Okay. I was trying to say order of operation. And likewise in B, U, V, and W are all vectors in R3. Okay, so it's possible to calculate another linear combination. So question C, I was trying to show you some properties, but you just remember when you see some brackets, the same as numbers, you compute the stuff inside the brackets first. It's kind of bad math, right? D is not defined. V minus Q is not defined. It's undefined. So because V is a vector in R3, V has 3 components, Q has 4 components. So we cannot subtract or add the 2 vectors. Simple enough. And before that, I want to mention some properties. Okay. Actually, probably we're not going to do too much of the abstract vector space. It's another course, the second course of linear algebra. But still, I want to mention some terms, some properties. Okay. You just imagine all the vectors are vectors in Rn. All the vectors are the vectors having n components. Or simplified, you just imagine all vectors are in R3. All vectors have 3 components. The first property says vector addition is commutative. I just said, so this time I'm not going to write it. Probably I wrote everything down when we talk about addition and scalar multiplication of matrices. So this time, if you want to write, you can write it down. But the first property is called vector addition is commutative. It means for any two vectors u plus v is always the same thing as v plus u. These two vectors can be any two vectors in Rn. You imagine n is R3. The second property says vector addition is associative. Okay. Still, I don't feel comfortable to. At least I'm going to write some keyword. Okay. I will copy this to the PowerPoint. I'm going to write some terms. Again, the first property, it says vector addition is commutative. The second property says vector addition is associative. I think I spelled this wrong. I said associative. Okay. The third property, now look at that. The third property says the zero vector is special in terms of addition. It has the property that the zero vector plus any vector is equal to any vector. Okay. I do not want to write down the term. But zero is called additive identity. You do not have to write that down. Okay. Now property number 4 is comparable to the thing that every number has a corresponding negative number. In numbers, we say the opposite of the number. Okay. So basically, in property number 4, okay. So now let's say u is the vector 1, 1, 2. Okay. So negative u is defined as -1 and then times u. It's actually the same thing as -1, -2. I'm trying to say negative u, you just get the negation of the two components. You have negative u. Okay. And property number 5 is kind of associativity for scalar multiplication. It's kind of associativity for scalar multiplication. Okay. I do not want to write down the term. It's not very precise. So property number 6. So there's a name for that. Property number 6. Okay. It means scalar multiplication is distributive over addition. I'm going to write down the full name. Scalar multiplication is distributive over vector addition. I will label the number. I was trying to interpret property number 6. 7, I do not write it down. Okay, it's kind of scalar multiplication is distributive over number addition. Okay. Property number 8 says 1 is special in scalar multiplication. It's comparable to number 1. A scalar multiple of 1 and any vector is equal to any vector. Okay. You just remember 1 is special for scalar multiplication. All these properties are simple to see, but you try to remember the 8 properties. In the future, if you need abstract vector spaces, probably I'm going to mention a little bit on that. These are the properties defining abstract vector spaces. If you do not fully understand what I mean, it doesn't matter. Okay, now an interesting question. This is the first proof you see in this course, and by the way, in this course you are going to see many proofs, and actually it's required for you to be able to reproduce many proofs. Now I'm going to prove that. So that's a property you learned in some geometry, probably in junior high school or high school. I don't know, but it's possible to use the knowledge of vectors to prove some geometric properties. I will show you how to prove this. I think on Friday's quiz you are going to see a proof, something like this. But don't worry too much. On Friday I'm going to make more comments on questions like that. But yeah. So because it's kind of the first proof, for Friday's thing, I will give you some hint. I just want you to be able to reproduce the proof. Okay. It's actually quite interesting. Now let's look at the setup. You have a triangle. Now I want you to recall something you learned a long time ago. Probably you learned in junior high school. Okay. You have a triangle. The triangle, whatever triangle, the setup is something like that. Whatever triangle. Okay. The triangle has three vertices. One vertex is A. Okay. Now let's say B is here. Now let's say C is here. That's the notation for triangle ABC. Okay. Now look at the setup. D is the midpoint of AB. And by the way, if I wrote a notation like this, it means this notation means the line segment AB. Now look at the mouse cursor. If you write a bar on top, this one means the line segment of AB. Without a bar, I think that's what you learned in PC curriculum. If you have a bar, so this one means line segment. So geometric line segment. So that's a line segment. Okay. If you do not write a bar, AB, so do not write a bar, this notation means the length of AB, how long. That's probably how you learned in high school or junior high school. Earlier I taught a course. The course is called Math for Teachers. Yeah, that's how I know the notation in here. In junior high school. Okay, now let's go back to the setup. D is the midpoint of AB. So now let's say, so D is here. You know what we mean by the midpoint. I think the term is simple enough. And the E is the midpoint of AC. E is the midpoint of AC. Now let's say E is here. So D and E, the 2 points, the midpoint of AB and the midpoint of AC, you connect D and E, you have a line segment. DE, right? I'm pretty sure you can recall a property you learned in high school. The line segment D is parallel to the line segment of BC for whatever triangle, okay? And the length of DE is half as long as BC. That's the property you learned in high school. In high school, you prove that using similar triangle, or you have seen that using similar triangle, right? But here we're going to use the knowledge of vectors to prove that. If you are confused with what I said, what do we mean by similar triangles? Similar triangles are two triangles having the same shape but different in sizes. The tiny triangle, the smaller triangle ADE, is actually similar to the bigger biggest triangle ABC, right? I was trying to help you recall the term. Of course, we do not use geometry to do this. We are doing vectors. Okay. Now we are going to prove the conclusion. Okay. To prove the line segment DE is indeed parallel to line segment BC and half as long. We are going to use vectors to do that. Okay. When you want to prove something, you write proof. You do not write solution. I'm trying to give you a kind of official mathematical proof. Actually, doing proof is the pure mathematicians are doing all the time. Okay. And by the way, I told you earlier, so this course requires some proof. It's part of the requirement. Okay. Now let's make some connection first. Okay. I give you two vectors. You tell me the relation. Okay. I think one vector I need is the vector BA. The vector BA. The vector with initial point of B and terminal point of A. And the other vector is the vector DA. Using the geometric meaning of scalar multiplication and vector addition. So anybody want to tell me the relation between these two vectors? Now look at the two vectors. Now look at the cursor. Okay, BA is the vector starting from B, terminating A. DA is a vector from D to A. Initial point is D. Yeah, that's right. So DA is half of BA. Okay, DA is half of BA. Or alternatively, you say it the other way around. I'm trying to write BA is equal to 2DA. Yeah, the same thing. The same thing as Ben told me. Sorry, I was trying to avoid saying names. It's because I'm recording lectures. I do not want to make your name too public. Okay, BA is 2DA. Okay. I think the next thing I need is the relation between AC and AE. Okay. The same story. AC is 2AE. That's the relation between two vectors as well. Right? Okay, I said BAAC. Okay, now I want you to tell me a relation between AB, BC, and AC. What is the relation between the vector BC and the vector BA and the vector AC? This time I give you three vectors. So please try to write something down, please. This time I give you three vectors, BC, BA, AC. Now I'm looking for a relation between the vectors equal. So what do we mean by equal? BC is equal to, I think you are trying to tell me BC, the vector BC is equal to BA plus AC. That's what you meant, right? Using the triangle rule. Okay, I will let you see. Okay, now look at the right hand side first. BA is from B to A, AC is from A to C. Now BA plus AC using the triangle rule we just learned. BC is equal to BA and plus AC, right? I'm going to label that using triangle. We'll continue the equation. Now I'm going to replace BA with 2DA. So BA is 2DA, right? And then plus I'm going to replace AC with 2AE. So do not forget the vector notations, okay? Using one of the properties we just learned. Now look at property number 6. Property number 6, okay. Now we are going to use the equation, the identity from the right hand side to the left hand side. From the right hand side to the left, it's kind of, you can take out k. It's kind of factor. So do you know what I mean? You can take a common scalar out of the two terms and getting that. By that we mean your k value is 2, you can kind of, so take 2 out of the two terms. You have 2 times dA, the vector dA, and then plus the vector AE. Using the properties, we summarize the properties, so in the future you can use the properties for any proof. So does that make sense? Okay. Now look at the sum of the two vectors in brackets. So in the brackets, so tell me dA plus AE. So how do you want to write dA plus AE? Using one vector? Please. I was trying to ask you, so what is DE? Yeah, DE is right. You look at the shaded triangle, okay? I was trying to ask you, you look at the tiny triangle. I was trying to ask you what's the answer to dA plus AE using the triangle rule again. So that's DE, right? That's DE. So you have to copy this 2 times DE, triangle rule again. Right. Okay, now look at two sides of the equation. BC is equal to DE. So this time I'm going to, that is the vector BC. That is the vector DE. Now we are saying BC is equal to 2DE. So does that mean the two vectors, does this imply two vectors are parallel? BC and DE, they differ by a scalar multiple. They are either in the same or in the reverse direction. Actually, they are in the same direction. It's because the scalar is positive. They are in the same direction. In particular, they are parallel. Now let's recall that two vectors are parallel if and only if one vector is a scalar multiple of the other vector. We mentioned earlier, right? And how do you want to compare the length of the two vectors? The length of DE is half of the length of BC, right? It's because the scalar is 2. We proved everything using one equation. That's how we prove things using using vectors. So does that make sense? Using this, we can see. So what? So we can see the line segment DE is parallel. That's the standard notation. Standard notation for parallel. The line segment DE is parallel to the line segment BC. Okay. And if you want to compare the length of DE is half of the length of BC. We see two things in using one vector equation. That's how we prove. That's how we prove things. Okay. To prove things, you just give step by step a perfect argument, saying why some equation, some identity is true, okay, or some conclusion is true. So we have seen the conclusion is true in this case, right? So that's how we prove. Again, on Friday you are going to see a similar thing to prove. I will give you enough hint on Friday. Okay? Something very similar to this. Any questions? Any questions on the proof? Simple enough. I went over the proof very slowly actually. If you don't have any questions, we'll move on to in terms of the handout, the next handout. In terms of the section, it's kind of the next section. We're going to talk about the definition of linear combination. That's actually one of the key definitions in the course. We're going to use linear combinations over and over again. Okay. Now look at the definition on the screen. Actually, the first question I want to go over is not that. Okay. I will copy the definition to the PowerPoint, and then I will ask you some questions, and then we try to answer some questions. Okay. On the screen you have the definition of linear combination. I know the definition is a little bit abstract for now, but I will show you the meaning using some particular vectors. So how about we just use some vectors in R2. Okay. I give you 3 vectors in R2. Okay. Now for example, I will give you 3 vectors in R2. Actually, the 3 vectors, the standard notation for a vector is I. I is a vector with the first component of 1 and the second component of 0. And another vector is called J. The two notations are standard. Okay, J is the vector with the first component of 0 and the second component of 1. I will give you one other vector. So now let's say the vector V, the vector with the first component of 1, the second component of 2, to make it simple. These are the 3 vectors in R2. These are the 3 vectors with 2 components, right? And by the way, IJ, they have a name. So these are we call these 2 guys the standard basis vectors in R2. So don't worry about the name for now. So later on the meaning will clear. Okay, will be clear. I mean. Okay, I did not even read the definition. I will tell you the meaning of the definition very shortly. Okay, but now my question is V a linear combination of I and J? Is V a linear combination of I and J? So by that I mean, so do not tell me yes or no right now. Okay, by that I mean, is it possible to write V as a number times I and then plus another number times J? if you can find two numbers so that v can be written as a number times I and then plus another number times j, and then we say v is a linear combination of I and j. Now I'm looking for the two numbers. I will copy the vectors. So vector v is 1, 2. Okay. Yeah. So 1, 2 is right. I think you got this. V is the vector 1, 2. Okay. And we are looking for two numbers so that the vector v can be written as a number times I. I is the vector 1, 0. And the j is the vector of 0, 1. I'm looking for another number. So basically, I'm looking for two question marks. I'm looking for two numbers so that the equation is valid. I think you guys just told me this number is 1, so this number is 2, right? One of the two numbers is 1. I'm trying to say this number is 1, so this number is 2. As long as we can find the two numbers satisfying the equation, then the given vector v is indeed a linear combination of I and j. Okay. Of I and j. Now let's go back to the definition. I'm trying to tell you the meaning of the definition. Okay. Now look at the definition. Okay. You imagine the vectors v1, v2, v up to vm are the vectors I and j. You imagine the vector v is the vector 1, 2 with two components 1, 2. Okay. We say v is a linear combination of v1, v2 up to vm. We say v is a vector of I and j. I'm trying to compare the general case and the special case. If we can find if there are numbers. By that we mean if we can find the numbers. So now let's say c1, c2 up to cm. So in this case the numbers 1, 1 and 2. Satisfying the equation, you compare the equations. Okay. As long as we can find the two numbers, then the answer is yes. Okay. V is a linear combination of I and j. Easy, right? And by the way, these two vectors I and j are called standard basis vectors. Standard basis vectors in R2. These vectors having the property that only one of the components is 1, all other components are zeros. These vectors are called standard basis vectors in R2. The meaning will be clear after we learn basis, linearly independence or independence, and so on. The meaning will be clear, but temporarily you just remember the name. Okay, so can I ask you one other question? Yeah, so that's the complete solution to this question. Okay. I will give you three other vectors in R2. Okay. One vector is the zero vector, and by the way, the zero vector is the vector with the two components 0. Okay, 0, 0. I forgot to mention that vector before. That's actually a special vector. Okay. If we interpret the vector as a position vector, so anybody want to tell me how to describe the position vector? To describe the vector, you have to tell me the direction and the length. Okay. Of course, the length is 0, right? The length is 0. The direction, so do not guess. I'm telling you the direction. Okay. The vector is a special vector represented by only one part. Now the problem is the direction. We interpret the direction of the zero vector to be in any direction. In any direction. I will tell you the meaning of that. Okay, zero vector. The zero vector is in the same direction as any other vector. That's what we meant by zero vector. That's the way we interpret the direction of the zero vector. Again, we do not say it has no directions. We just say it has any direction. Okay? It's in the same direction as any other vector. I think I made the whole thing clear. The zero vector in R2. Okay. I also give you I and j. Okay. So now I say I is the vector 1 0, j is the vector 0 1. Okay. These are the vectors in R2. Now let's know my question. Now we concentrate on the concept of linear combination. Now let's know my question. Okay. I think the second vector is the vector j. I forgot to give you the notation. Is the zero vector a linear combination of I and j? Now I'm going to repeat my question. Okay. Is the zero vector a linear combination of I and j? If it is, how do you tell me the two coefficients? To determine if the zero vector is a linear combination of I and j, all we need is to think, is it possible to write the zero vector as a number times I and then plus another number times j? What are the two numbers? As long as you can choose any two numbers satisfying the equation, then the answer is yes. What are the two numbers? What are the two numbers? So please. So anybody try to write the two numbers on the screen? What are the two numbers? Yeah, two numbers are both 0. 0 and 0. Okay, 0 and 0. Okay. These two numbers, they can be zeros, right? As long as you can get the two numbers, and then the answer is yes. By that I mean the zero vector is indeed a linear combination of the two vectors I and j. Okay. Good enough? Okay. I'm going to write it down. I thought of something. Okay. Zero vector is a linear combination of I and j. So because the zero vector can be written as a linear combination of I and j as 0, the number 0, so times I, right? And then plus another number 0, and then times j. Okay, to understand the meaning of the concept, I'm going to ask you one other question. Okay, so this time I will give you three vectors, any three vectors, u, v, and w, in any Rn. Now let's know my question. Now listen to my question carefully. Is u a vector? Now let me try again. Is u a linear combination of u, v, and w? Is u a vector? Is u a linear combination of u, v, and w? I'm going to write the question down. Okay. Is u a linear combination of u, v, and w? I don't know what I was trying to write. Is U a linear combination of U, V, and W? By that we mean, is it possible to write U as a number times U and then plus another number times V and then plus another number times W? All these questions are designed for the meaning of the linear combination. We're not doing any calculations yet. Is U a linear combination of U, V, and W? If yes, what are the numbers? What are the 3 question marks? So please. Is it possible to write U as a number times U plus another number times V plus another number times W? Simple. So please, try to write something down, please. What are the numbers? I'm looking for 3 numbers. As long as you can find 3 numbers satisfying the equation, then the answer is yes. Anybody? Yes. So what are the numbers? Yeah, 1, 0, 0. All right. Okay. Okay. U can be written as a linear. U can be written as a linear combination of U, V, and W as 1 times U, 0 plus 0 times V, and then plus 0 times W. So that makes sense? 1, 1, 1 will not work. I think 1, 0, 0 works. 1, 1, 1 will not work. You just choose 3 particular vectors. I know the question might be a little bit abstract to some of you guys. So because I'm trying to use U, V, and W, so with no, of course they have components, but I did not give you components. It can represent any vectors. So the answer is yes. The numbers you can choose are 1, 1, 0, and 0. Okay. Again, all these questions are designed to understand the meaning of the linear combination.